Hi, everyone. I'm Lloyd Gum, Global Director of Marketing with the Zappi Group of Companies. I'd like to welcome you to day 2 of the Future of Electrification conference and this keynote session. Remember that the session is being recorded and will be available to watch on demand following the live presentation. If you have any questions during this session, please add them to the Q&A. You can find that tab to the right of your screen. And note that those are sent privately. Well, with that, I'd like to introduce our keynote speaker for today. I'd like to welcome Dr. Giorgio Rizzoni, Professor of Mechanical and Aerospace Engineering and Electrical and Computer Engineering at Ohio State University, where he is also the Ford Motor Company Chair in Electromechanical Systems. He'll be speaking about challenges and opportunities in electrification of the commercial, industrial, and utility vehicle sector. Really appreciate you being here. Dr. Rizzoni, please go ahead.
Thank you very kindly, Lloyd, and it's a pleasure to be here. It really is a great honor to have been invited to speak. Due parole in italiano per salutare i colleghi italiani. La presentazione la farò in inglese, magari in futuro ci riusciremo a incontrare anche di persona. So back to English now, and I am going to share my screen and talk a little bit about some of the prospects that we see in this very important industrial sector. I am going through the steps here of sharing the window. I think we should be ready to go. So, as Lloyd mentioned, powering the future, challenges and opportunities in the electrification of commercial and industrial vehicles. This is a sector in which I have worked for many years. My function is to perform research in collaboration with industrial partners and government agencies, but also, perhaps more important, really my primary mission is to work on the education of future engineers, many of whom work in your industrial sector. I wanted to say a quick thank you to two valuable colleagues, Dr. Manfredi Villani and Dr. Michele Giuliani, who have both contributed to the preparation of this presentation. So here is a broad outline. I'm going to talk about electrification in a big picture sense. I always like to begin these conversations by presenting the larger energy and emissions picture. We'll talk a little bit about challenges and opportunities, and I will draw some conclusions. So I am based in the United States. I've worked here for my entire adult career. So I'm using US data to represent some of the ideas that I want to share with you. And I always like to begin with the big picture of energy production. And this picture, which is produced annually, this data is published annually by the Lawrence Livermore National Laboratory, has on the left-hand side the primary energy sources. You can see solar, nuclear, hydro, all the way down to petroleum. And on the right side, if you focus on the four pink boxes, the four major uses of this energy: residential, commercial, industrial, and transportation. In between these, there is electricity generation, which is a very important intermediate sector. And the emphasis I wanted to draw in this picture is that if you look at 2011, so a bit more than a decade ago, almost a decade and a half ago now, you notice that in the United States, about half of the electricity produced was generated from coal-fired power plants. And when you look at the transportation sector, which is an important part of our conversation today, you notice that a large fraction, more than 95% of the energy used in transportation, really is based on petroleum-based fuels. Let's take a leap forward. The most recent data that has been published by Lawrence Livermore National Lab illustrates today's situation. So this is a 12-year time span between the two pictures. What do we see? Well, electricity generation has changed dramatically, at least in the United States. You notice now that what used to be about 50% of electricity production based on coal-fired power plants is now less than 25% coal-based. Natural gas has replaced a substantial amount of that electricity production, and solar and wind power are doing a little, but not as much as perhaps we would like to. But the reduction in carbon emissions in electricity generation has been a clear trend, a clear theme in the development of energy systems over the past dozen years or so. What is important to emphasize here is that transportation is still very much dependent on petroleum. Over the past 12 years or so, perhaps the biggest difference is the increase in the use of biofuels, fuels from biomass. What impact does that have on greenhouse gas emissions? Well, one of the consequences of this has been that while the electric power sector had historically been the largest producer of carbon dioxide and greenhouse gas emissions, over the past few years, transportation has clearly become the responsible for the largest fraction of greenhouse gas emissions. Certainly true in the US, but I think that this picture is not too dissimilar in the European Union. One of the important points here is that about a third of greenhouse gas emissions are associated with transportation. And once again, about 1/3 of that is associated with medium and heavy duty on-road vehicles and off-road vehicles. So altogether, about a little more than 10% of greenhouse gas emissions are in that sector. A snapshot, just a big picture to show you a bird's eye view of annual carbon dioxide emissions. And you can see that China and the United States are responsible for, give or take, when you add the two of them, almost 50% of the total carbon dioxide emissions worldwide. So we wish to reduce greenhouse gas emissions. What are the pathways that are available to us? Well, there are really, in my mind, three ways of thinking about this problem. We can address the energy sources. For example, in electricity generation, transitioning from carbon-based fuels to non-carbon-based energy sources, such as wind, solar, geothermal, hydroelectric, et cetera, et cetera. A second very important component of this is energy efficiency. Can we, by design, the use of different technologies, the use of advanced materials, can we develop more fuel-efficient vehicles to perform the duties that we wish these vehicles to perform? And then finally, operating practices. It's not just the energy efficiency of the vehicles and the fuels we use to power them, but as an example, can we be more intelligent about how we ship freight, for example? Could we minimize the so-called empty miles in freight transportation? This is just an example. But if we reduce the number of miles covered by trucks that are not carrying a load, that will be, from an operational perspective, a more efficient use of energy. So let me say a few words, and I'll give you the big picture, and I'll divide it between on-road and off-road commercial vehicles. Once again, I am largely going to use the US data and figures as a starting point for my explanations, because that is what I have more immediate access to. But I think that many of these conclusions could be easily translated to numbers that are relevant to the EU, for example. If you take a look at on-road commercial vehicles in the United States, there are about 23 million commercial vehicles on the road. And the way we represent them in the US is by classes. Class 1 and Class 2A are passenger vehicles and light trucks. From class 2B up, we are talking about commercial vehicles. Very important to understand that while long haul tractors, the big tractor trailer vehicles that drive coast to coast every day, they only represent about 9% of the total fleet. They represent almost 50% of greenhouse gas and, for example, NOx emissions, criteria emissions. It's important to understand that these vehicles are also predominantly fueled by diesel today. If you look at the medium and heavy duty market segmentation by class here, you will see again a similar picture, a little bit more detailed. I won't read through all of these, the specifics of all of these numbers, but I again want to point out that when you look at it in terms of vehicle miles traveled and energy consumed, which of course correlates with greenhouse gas emissions, the class 7-8 long haul freight are really responsible for the majority. But there are a lot of other functions that are performed by vehicles that have different missions, from regional freight movement to local functions to utility functions. So I won't go into the details of this table, but I will make a few comments. I want to point out that over the years, there has been a clear timeline for emissions regulations for heavy-duty compression ignition, that is diesel engines, across major regions of the world. So you can see here the European Union, California, Japan, China, South Korea, India. And it is very important to understand that there is a trend, a desire to reduce criteria emissions. So here you were talking about particulate matter, NOx emissions, and this has led to a push for advanced after-treatment systems and alternative powertrain technologies to enable a future for diesel engines. Some of these regulations are especially strict. In the US, the state of California has its own set of regulations in this domain. But that was with respect to criteria emissions. Carbon dioxide is a separate topic. And in this table, you see, again, a roadmap starting from a few years ago, 2020, with projections about how different regions of the world, and notice that in this picture, I've actually separated California from the rest of the United States. What are the projections for CO2 emissions in heavy-duty vehicles? And you can see that the goal is to reduce CO2 emissions, providing a strong motivation, of course, for alternative technologies, including electrification by the use of batteries and by the use of hydrogen fuel cells. The picture for off-road industrial vehicles is perhaps a little bit more colorful and diverse. The number of functions that are performed by these vehicles is virtually uncountable. On-road vehicles, they do one of two things. They either transport people or freight. Off-road industrial vehicles perform a number of critical functions in our economies. They are involved in construction, industrial applications, agriculture, lawn and garden care, recreational activities, logging, mining. And here is a picture that shows you from a fuel consumption perspective how these different sectors are represented in two ways. One is by millions of barrels of petroleum used, and the other one, if you look at the color code, the darker blue are small engines, vehicles that are powered by less than 50 horsepower. So for example, it's clear that in the lawn and garden sector, that's the overwhelming majority. Then there are medium range propulsion systems in the 50 to 175 horsepower range, and then the larger engines. We can see here that construction is the largest represents the largest fraction of fuel consumption in this off-highway sector. Industrial and agriculture, and surprisingly, perhaps lawn and garden functions are not that far behind. If you look at a comparison of fleet count versus the number of hours of usage of these vehicles, which correlates with the energy and greenhouse gas emissions, you can see that construction, agriculture, industrial applications, and lawn and garden, again, I repeat, a little bit surprising maybe, together are probably close to 90% of the total energy usage in greenhouse gas emissions. So this is an important consideration, and one of the questions that we ask ourselves is, how can we address this, and what are some of the alternatives that we have available to, for future greenhouse gas emissions reduction? This next picture will take a moment to analyze in a little bit of detail. And what we are trying to understand is, what are the opportunities for using alternative energy sources and alternative technologies to reduce greenhouse gas emissions relative to conventional diesel. So life cycle greenhouse gas emissions, a 70% reduction with respect to a conventional diesel, is marked by this vertical dashed orange line. And I have picked three different cases in which I want to illustrate the opportunities that we have and what is really truly the impact of alternative fuels in this case. So on this line, we're looking at what would happen if we used natural gas-fired power plants to generate electricity, and what if then we had carbon capture and storage at the production plant, at the power plant, to generate what is commonly referred to as blue electricity. And then imagine using this blue electricity to power your industrial vehicles, your commercial vehicles. What you can see here is that natural gas combustion with carbon capture and storage is almost, but not quite, 70% greenhouse gas reduction capable. If I now take the same fuel, natural gas, but now what I'm going to do is simply take the electricity output from a natural gas-fired power plant and do not do carbon capture and storage, you can say, of course, that in this case, that electricity produces significant greenhouse gas emissions, and by itself, it is really not close to that 70% goal. And the other point that I wanted to make is that if I use diesel fuel, the important thing to understand is that there are three phases in the greenhouse gas emissions of a vehicle. One of them is the feedstock itself, obtaining the feedstock. The second one is converting that feedstock into a usable fuel, refining. And the third one is the use phase. So if I'm using a diesel engine powered vehicle, my emissions are largely generated in the use phase. When I am using natural gas or other alternative fuels, my emissions will be highly concentrated in the feedstock extraction and energy conversion process. It's very important to understand that there are upstream and downstream consequences. I will make a brief comment about the fact that around the world, regulations for both criteria emissions of off-highway vehicles as well as CO2 or greenhouse gas emissions are evolving very rapidly. I believe that you, the participants in this conference, will have access to the material that I'm presenting to you. So it's not the time to delve into the details here, but I want to emphasize that at the moment, the projection, especially as we go to what is referred to as the stage 5 criteria emissions regulations, is that we're looking at stricter and stricter NOx and particle number limits with a focus on air quality, of course, for all vehicles used in the off-highway sector. And similarly, in the United States, we have, we call it Tier 5. There are similarly very detailed and increasingly strict regulations for NOx and particulate matter emissions. So, summary of this first part of our conversation is that it is a complex world. We have millions and millions of commercial vehicles operating every day in factories, farm fields, highways, and freeways. And they perform important functions for our economy. We depend on them. The ability to move freight and people is fundamental key to economic development. And there are significant challenges in finding technological solutions that are going to help us perform these functions and at the same time reduce greenhouse gas emissions and improve air quality. So what I'm going to do next is to talk a little bit about two of the technologies that are typically associated with electrification, batteries and hydrogen. And I will begin with talking about where the landscape of battery research and development and also battery commercial development is today. And I will begin by saying that there are really 4 elements that are important and must be considered. One is there needs to be a strategy for how to deploy electrification of vehicles that are powered by batteries. That requires having a charging infrastructure that is capable of supplying the energy that is needed outside the fence and behind the fence. What do I mean by that? Some of it could be public recharging infrastructure in the roadways. Some of it would be dedicated to the specific functions of a port or of a factory plant, for example. This will require a tight integration between the electric power grid and the charging infrastructure and an understanding of how vehicles need to take advantage of electric power. And we'll talk a little bit about the life cycle of batteries as well. A few years ago, in 2021, the U.S. Department of Energy produced a national blueprint for lithium batteries. This is a document that is available in the public domain. If you do an internet search on those words, you will find it easily. But I want to point out that it is really important to understand that there are stages to the development and deployment of battery electric vehicle technologies that are dependent on how lithium batteries are produced. And that goes from the top level to the raw materials extraction. Which raw materials are used for the manufacture of batteries is extremely important. Lithium, of course, today is an important element. We're still strongly dependent on cobalt and nickel for many battery chemistries, and graphite, of course, is an important element. So where those raw materials are, the supply chain, the availability of materials, all of this is extremely important. But that's one piece. There is an intermediate midstream step that is extremely important. There is a substantial amount of materials processing that needs to take place. We call it beneficiation. For example, lithium that may be extracted in the form of brine or ore from a lithium mine needs to be refined, much like we refine petroleum into gasoline or diesel fuel. And this processing is an energy intensive process that also has environmental consequences. It requires water. It's not a simple thing to do. That refined lithium then moves on, allows us to move on to the next step, which is the manufacturing of cells. There has been a lot of talk about developing the capability for doing cell production and manufacturing in Europe, in North America, but we must remember that raw materials production and materials processing today occur, especially the materials processing, which is largely based in China, they occur outside of the boundaries of our countries, and there is a substantial amount of logistics and movement of these materials that is part of the process. Then we go into the downstream segment in which packs are manufactured and then used for electric vehicles, stationary energy storage, aviation, defense applications, whatever they may be. And we must not forget the end-of-life recycling and reuse. So this basically represents the complete cycle. There are challenges to this, as I have mentioned. Securing access to both raw and refined materials, looking into alternatives for critical minerals. Today, the two most widely used chemistries in lithium-ion batteries are either based on iron phosphates and graphite or on lithium, nickel, manganese, cobalt chemistries, also with graphite anodes. So there is a question, here is a US perspective as to where these materials are, what are the known reserves. For example, here are the world reserves of lithium, cobalt, nickel, manganese. And you can see that some materials are more challenging than others, cobalt, for example. So the materials processing or refining or beneficiation of these materials is a very important element, and having the ability to do that in different regions of the world will be very important. I highlighted in red end-of-life reuse and critical materials recycling, with the goal of having a cost-positive recycling process that would make it viable to actually implement recycling strategies. And in general, we're all focused on developing and transforming the workforce so as to enable all of these processes. There are some key R&D challenges that are still important in the world of lithium batteries. The cost of batteries today is trending towards this $100 per kilowatt hour. For a long time, this has been considered a goal that would make a battery-powered electric vehicle propulsion system achieve cost parity with an internal combustion engine-powered propulsion system. There are performance issues. The performance of batteries in terms of their behavior at low and high temperature or when subject to fast charging is a very important topic of research. We're not finished exploring how to optimize the behavior of batteries under these conditions. Life, I always like to say batteries are electrochemical systems like the human body, and like the human body, batteries age. And abuse tolerance, and there are some safety considerations with respect to that. I'll give a brief example here of a project we're working on in collaboration with the US Department of Energy and Oak Ridge National Lab, in which we are exploring what will it take to enable battery electric trucks in drayage applications. Drayage trucks are the trucks that move freight from a ship. And here the example is based on the port of Savannah in the south of the United States on the East Coast. And these are the trucks that move containers off of ships and deliver them to distribution centers to then be shipped around the rest of the nation. And you can see that these drayage trucks, there is a desire to have them, to have zero emissions drayage truck in ports. And so some of the questions that we're addressing here are, on one hand, the requirement for charging infrastructure. On the other hand, how do you optimize the performance and longevity of the batteries that you would use in these applications? You could imagine, think of an application that would be relevant in your industrial sector. You could similarly define the duty cycles and mission profiles of your application and study the feasibility of transitioning to battery electric propulsion. There is a lot of interest, there has been, it kind of goes around up and down in cycles, on hydrogen. And hydrogen, it must be remarked upfront that hydrogen is an energy storage medium. It's an energy vector. It is not a fuel, because hydrogen is largely produced by an energy conversion process. So there are many questions associated with hydrogen, which is how is it produced, and then how is it converted into energy? And the notion then is to use fuel cells, which are electrochemical energy converters that perform direct conversion of hydrogen into electricity. Well, infrastructure, of course, is an issue, just as is the case with upgrades and improvements to the electric power grid to enable charging. If we're seriously thinking about hydrogen as an energy vector for vehicles of the future, we would need to have the appropriate infrastructure. A couple of words about hydrogen fuel cells. They are capable of achieving higher efficiencies than internal combustion engines. They are zero emissions at the point of use, and generally speaking, relatively simpler. The stack itself does not really have any moving parts. But there are challenges. Cost across the board, from the materials to the production of these systems. Their durability is very important. Just as we have to deal with battery aging, we need to deal with the durability of membranes and catalysts. And most important, the biggest challenge is infrastructure to enable hydrogen refueling. I'll say make a couple of engineering comments about some of the challenges that perhaps are sometimes overlooked with regard to fuel cell. They produce a lot of heat. While it is true that a fuel cell can be 50% efficient, the other 50% is heat generation. And unlike in an internal combustion engine, where amply 1/3 of the heat produced by the engine exits through an exhaust tailpipe system, there is in a fuel cell, we have to deal with cooling systems that have to handle a substantial amount of power. Imagine that a 100 kilowatt fuel cell system, if you're producing 100 kilowatts of electric power, you'll produce 100 kilowatts of heat at 50% efficiency. So imagine some of the challenges with the fueling systems. Very important to understand that humidification of the membrane in proton electrolyte membrane fuel cells is another important challenge that needs to be addressed. The gases that are used in the energy conversion must be humidified upstream of the stack. We need to achieve a water balance in the system, and temperature, ambient temperature, of course, has an impact of that. And finally, degradation and aging is a substantial challenge in the world of fuel cells. Fuel cells employ catalysts to improve the conversion efficiency, but these catalysts can degrade and become less functional over time. And so there are issues here with regard to the aging of fuel cells that are analogous in some ways to those related to the aging of batteries. When I speak to my colleagues in the commercial vehicle sector, there is sort of a general understanding that, by golly, if we can get this hydrogen to cost $1 to $2 a kilogram and to be available to have an infrastructure capable of delivering it, it would become an attractive alternative to diesel fuel, for example. So how do we produce hydrogen? And here is what's very important. This is a very important point that ties in to some of the things that I said earlier. One way of producing hydrogen is by electrolysis of water. Well, that of course requires electricity. And if you look at where we are today in the United States, we're looking at, roughly speaking, the production cost of hydrogen using electrolysis of water has three components: the electricity that is used, the capital cost of creating the infrastructure, and operations and maintenance. The US Department of Energy has a target, but a target is a wish. It is not necessarily an executable plan to arrive at $1 per kilogram hydrogen from water electrolysis, which would require a significant reduction in the cost of electricity, in the capital cost, and in operations and maintenance. So the point is that hydrogen production by electrolysis is something that is desirable, but will require significant cost reduction before it becomes attractive. Let me also say that the color of the electricity that you produce or that you use in the production of hydrogen is extremely important, because if I am producing electricity by burning coal, then frankly, I'm not sure that it's a good idea to use the coal-fired electricity to produce hydrogen. There is an upstream emissions cost. Today, however, I talked about electrolysis, but today most hydrogen in the United States is clearly upwards of 95%, is produced by steam reforming of natural gas. So if we use methane feedstocks, there is a immediate benefit, which is that its baseline cost is already some close to the target. And the idea of arriving at a 2031 target that the US Department of Energy has set of $1 per kilogram is actually much closer. But understand that this would make sense in a context in which the steam reforming of methane or natural gas is accompanied by carbon capture and storage. Otherwise, the upstream emissions would be too large. Electrification, of course, can take place in multiple forms. And I have some examples here of vehicles that are actually on the road in the United States. These are special vehicles that perform functions in class 3, battery electric small truck, class 6, a larger battery electric vehicle used as a refuse hauling truck. Here in the US, we see these UPS trucks everywhere. This is actually an EV. And here is a utility truck. And I'm going to give you a brief example of this utility truck to make a couple of important points. Odyne is a company that actually, and this data is a few years old. I'm not sure by now how many of these vehicles they have. These are plug-in hybrid electric medium-duty utility trucks. And the point I want to make with this slide is very important. There is an issue of mission profile, which in every commercial application, on highway or off highway, is critical to understanding what architecture is most appropriate for that specific use case. So in the case of these utility trucks, look at what happens. In the drive, the vehicle spends a little less than a quarter of its time in drive mode. It spends almost 40% of its time in electric power takeoff. That is, it uses the battery to provide electric power to perform the functions of this vehicle with the engine off and the vehicle stationary. And about 14% of the time, we do power takeoff, but this is done with the engine on. Small fraction of the time charging from the engine to the battery pack, and then idle parking is almost a quarter of the time. If you look, however, this is the time associated with the duty cycle of the vehicle. What about energy consumption? About 50% of the energy consumption is associated with the drive mode and about 1/3 with the engine on PTO. So these are considerations. This is just an example of a utility truck, but imagine whatever application may be relevant to you, understanding the duty cycle is of critical importance. And so in a study done relatively recently, a few years ago, for other applications, bucket trucks like the one I showed you, parcel delivery, food delivery, school bus, there is a question of what is the potential for energy use reduction that is can be significant for these specialized applications. But then there is also the question of what are the benefits. And these benefits could be achieved in a variety of ways. In this particular case, here is a vocational truck. A mild hybrid powertrain may be, in fact, enough to achieve a significant fuel consumption, over 20% for this particular application, without having to invest too much in the battery pack for the vehicle. And this brings up the subject of total cost of ownership. I'll make a comment related to the customer preferences in purchasing a personal vehicle for private use. The looks, the color of the vehicle, the convenience features are the most important things sometimes. But for vehicles that are used in the commercial sector, on or off highway, the total cost of ownership is and should be an essential criterion in making decisions about the architecture of the propulsion system and the basic selection of energy sources and fuels for a vehicle. And it's important to understand that total cost of ownership is the cost of the vehicle, the cost of the financing when a fleet of vehicles is purchased, the cost of the fuel is just one of the elements, insurance elements, maintenance and repair, taxation, the taxation structure in the specific country where the vehicle is used, changes in payload. Will a battery electric vehicle reduce the payload because of the increase in mass caused by the battery? And then in general, labor and time. Do I have to spend time charging the vehicle, for example? Very important to understand the total cost of ownership. Here I have a simple example where when you look at maintenance breakdown, for example, there is a clear advantage to a battery electric vehicle, much lower maintenance costs. But of course, there are other elements that need to be considered in addition, of course, to maintenance. There are also risk factors, and there are uncertainties in utilizing vehicles that have alternative powertrains. For example, if the vehicle uses a battery, what if I have to replace the battery? That's a potentially very expensive proposition. What's the initial price differential? Will there be incentives, tax rebates, and the like? What about the price of fuel? Here in the United States, the fluctuations in diesel prices are substantial. And from one month to the next, your benefit in having an electric solution may be nullified by a decrease in diesel fuel prices. Similarly, electricity prices. Annual mileage. Do we know exactly what kind of duty cycles the vehicle performance, how much it will be used, and so on. These are all observations that have an impact on payback period. So if I need to make a larger investment in purchasing an advanced or an alternative powertrain vehicle, what's my payback, and what is the uncertainty in reaching this payback point. So these are all important considerations. And I will close with a very brief comment about the fact that there are some fascinating opportunities available to us. I have had the pleasure of working for a number of years now on a program called Next Car. It's focused on passenger vehicles, but the focus is how is it possible to utilize knowledge of the duty cycle of the vehicle and of its surrounding environment to achieve energy efficiency improvements. And this, I think, is something that we clearly demonstrated has potential benefits in passenger vehicles, utilizing sensing and infrastructure provided information and the methods of artificial intelligence, machine learning, and advanced control ideas. We demonstrated that it is possible to achieve operational improvements of the order of 20% in passenger vehicles. And some of these things may well be achievable in commercial vehicles as well. We're currently working on the next phase of this project, which involves actually a vehicle that is automated. So in addition to connectivity with the infrastructure, driving automation may also provide additional benefits. So I will stop here with a brief conclusion by simply saying that it's a very exciting time, certainly from the perspective of someone who spends his days engaging in research programs with the automotive industry and the commercial vehicle industry. There are many opportunities, many challenges, a lot of work ahead of us. And I will be delighted to now engage in a conversation with you and answer any questions you might have. Thank you very kindly for attending this presentation.
Dr. Rizzoni, thank you for that presentation. It was very good. Thanks for sharing your work and your perspectives. Question on alternatives to petroleum-based fuels. What do you see going forward? Anything emerging?
Yeah, the petroleum conversation is quite interesting, and I'll use as an example the aviation sectors. We might argue that a certain industrial application may transition from a diesel engine powered vehicle to a battery electric powered vehicle. Pretty straightforward, but I don't think that any of us imagines that airplanes will ever cross the Atlantic Ocean or the Pacific Ocean on lithium batteries. I think we will all agree that that's unlikely, right? So the aviation industry is very much looking at sustainable fuels. So the problem with engines is not the engine itself. Internal combustion engines are great machines. It's the fuel we use to power them. If we extract the fossil fuel from underground and then combust it, we have a net addition of CO2 into the atmosphere. What if we were able to synthetically produce what are called e-fuels that are developed by producing hydrogen from carbon-free sources, wind, solar, and reacting that hydrogen with carbon dioxide extracted from the atmosphere so that we can create a closed cycle. We do not add any further carbon dioxide into the atmosphere. We extract it, react it with hydrogen that is produced from carbon-free sources, and we can produce, our chemical engineering friends know how to produce pretty close to net zero carbon liquid fuels that behave very much like petroleum-based fuels. So there is a lot of talk about what if we transition to these e-fuels, what are the scaling up of these processes. They've been demonstrated, they exist, but how do we scale them up and how can we create a production, refining, and distribution system that might make these fuels an alternative to diesel for vehicles that cannot benefit from electrification. Simple example, not just airplanes, but a coast-to-coast truck operating between the East Coast and the West Coast, Class 8 tractor trailer system. Difficult to imagine also to do that on batteries, for example. So I think that there is a lot of work in that direction. We're not close to having commercially available e-fuels, but there are some pilot scale examples that are advancing.
Thank you. Question 2, there's a lot of talk about alternatives to lithium ion batteries. We hear a lot of that. Based on what you're saying, what do you think the most realistic technologies are?
First of all, in the world of lithium-ion batteries themselves, there is this continuous improvement in electrolytes, electrode materials, production process, and so on. So there is continuous improvement in the sense of lowering cost and improving the life and performance of today's lithium batteries. Probably the next step will be batteries with solid-state electrolytes that will allow us to have safer, longer-lasting lithium batteries. There's a lot of talk about solid-state batteries. The truth is that we're not quite at commercial production at scale. We're approaching that. There has been a lot of talk about sodium-ion batteries. You look at the periodic table of the elements and you say, oh, okay, hydrogen, lithium is great, a very lightweight element. What's close to it? Well, sodium is. Could we make a sodium-ion batteries? They're beginning to go into production. I see sodium-ion batteries as a clear candidate for stationary applications. Their energy density is not as good as lithium. Therefore, a battery that might be this big with lithium might become this large with sodium. But sodium is widely abundant, and so there are many benefits. The challenge with new chemistries is when you read in the media, which we do every week probably, someone has come up with this new wonderful battery technology. It's one thing to do it in a laboratory. It's another thing to do it in a pilot scale, small limited production capability like we have at our university. And it's a completely different thing to create the entire supply chain and to scale up this to true commercial production. So if we convince ourselves that we have a magical material, call it unobtainium, okay? We have this beautiful unobtainium battery that has all the characteristics we want. I would say that the time frame to have a new battery demonstrated in a laboratory today to go into production is probably a 7 to 10 year life cycle, before you can get to large scale production. How to accelerate these processes, we're all working on it, but the truth is that it takes time because you need to develop a supply chain, the manufacturing processes, and so it's a complex world. And I think that it's very important to take a long view of these things. There is no quick and easy solution.
Okay, got it. So don't get too excited about press releases on the first.
I would say, yeah, read them with interest, but don't get too excited. I agree. Yeah.
Question from the audience. This is the last one we have time for.
Sure.
It's a system architecture question. Which voltage buses do you foresee being adopted? 400, 800 volts? And then a follow-on question. Do we expect battery developments of 1200 volt plus?
Yeah. So I would say that there is a definite trend to move up in voltage. There are efficiencies that result from increasing the voltage, lowering the current, reduces ohmic losses. There are challenges that go with higher voltages. So I see a clear movement from, especially in the commercial vehicle sectors, towards 600, 800 volt DC bus implementations. We have clearly seen that some electrification work that has been done in the aviation industry, we've done some work with NASA ourselves, is moving all the way up to 2 kilovolts. As you go higher in voltage, you begin to have some issues that have to do with safety, partial discharge, and other things. But I think that aiming, going in the direction of 800 volts would be a very reasonable thing to do for the larger applications. And the second part of the question was,
do you expect battery developments supporting 1200 volt plus?
yeah, I think that the challenge as you go up in voltage is that you need more cells in series. I mean, in the end, the voltage is added up, it's created by adding up cells in series. So obviously, you're going to have to deal with the size of battery packs as you go higher in voltage as well. So the two things are somewhat connected. I think that from the days of 300-400 volts, we're clearly moving to a world of 600 to 800 volts application. By the time you get to a kilovolt, I think you begin to face some interesting challenges.
Okay. Well, thank you for that. Yeah, thank you. And for the all attendees, thank you for attending this session. You can join the next sessions from the lobby. But Dr. Rizzoni, thank you very much. Grazie mille. Appreciate your presentation.
Grazie a voi, è stato un piacere. Thank you very much.